The ocean is planet Earth's greatest wilderness. A sheet of endless blue offers no hints at the wonders held within. But below, this world is far from uniform. From the high seas to the shallows, from the surface to the deep, hidden beneath the waves is a symphony of life and mystery. It binds far-flung ecosystems together through currents and systems that span tens of thousands of kilometers, where changes in one extreme of the ocean affect the processes of another. Of the ocean's many domains, the deep stands as one of the last frontiers of exploration. It may hold the key to understanding our planet's past, present, and future. It's a world of perpetual darkness, home to obscurities adrift in an endless void or clinging to alien oases, where the processes, inhabitants, and environments remain poorly understood to this day. These are the least known areas of our planet, but this is beginning to change. In 2009, the philanthropic non-profit Schmidt Ocean Institute was established with a mission to advance ocean science through state-of-the-art technology and open sharing of knowledge, fostering a deeper understanding of the world beneath the waves. Across 11 years at sea, scientists on board their first vessel discovered never-before-seen wonders throughout the world ocean. But the ambitions of the Institute outgrew capabilities. In 2023, the Institute set sail with its new vessel for their boldest year of discovery to date. This is a newly refitted 110-meter global-class research vessel, purpose-built to push the frontiers of deep ocean exploration once and for all. The vessel is designed around its instruments, outfitted with 2 moon pools, a 150-ton crane, over 200 square meters of lab space, high-resolution sonars for ocean mapping, and a hangar from which the Institute's remotely operated vehicle, Sebastian, is deployed. ROV Sebastian, a robot capable of diving to 4,500 meters below the ocean surface, opens a window into this realm for all to see. Manipulator arms collect samples and an umbilical cable tethers the ROV to the ship, supplying power and relaying data and imagery to the surface where it's broadcast around the world in real time. Throughout 2023, across 9 expeditions spanning wildly different environments, teams aboard deployed new technologies, systems and approaches to map the seafloor and uncover new frontiers of biodiversity in the deep's most extreme habitats. In its first year alone, the vessel enabled scientists to make groundbreaking discoveries that are redefining our understanding of life in the deep. Living cities at depths of 2 kilometers or more, active nurseries where little-known species gather in great abundance to brood and spawn, and entirely new ecosystems thriving in an underworld beneath the sea. These are just some of the discoveries made possible by. Hello and welcome aboard our dynamic, inclusive and interdisciplinary ocean research and exploration vessel. The mission of this vessel is to foster discoveries needed to understand our ocean, sustain life, and ensure the health of our planet. As you boldly explore our unknown ocean, these are the stories of, and its first chapter, into a lifetime of exploration. First tale is one of discovery. In March, the vessel was bound for the Mid-Atlantic Ridge, a site where 23 years prior, scientists discovered a system of hydrothermal vents unlike anything seen before. The vent system, named Lost City, became the target of the team as they hunted for more like it. Tracking down sites of potential venting involved a combination of high-tech strategies. The first step was to map with the ship, creating a base map that highlighted ridge crests, seamounts or fault zones, features that create pathways for hot water to travel from deep within the crust to the seafloor. This allowed the team to lay out survey missions covering the volcano summit areas of interest. On Sebastian's very first dive from at a previously unexplored portion of the Puy de Fou seamount, the mapping data pointed to the existence of vents. From the gloom, silhouetted structures emerged. Chimneys spewing thick plumes of dark smoke formed from the precipitation of sulfides. These black smoke events, never seen before, hosted vibrant life. Hordes of swarming shrimp and hairy white yeti crabs farmed bacterial colonies on their shells, coexisting among chimneys of minerals and cathedrals of basalt. Every dive brought new surprises. Multiple high-temperature smoke events were discovered in remote locations teeming with activity and life. The chemical composition found at these vents closely resembles the conditions that may have facilitated the dawn of life on Earth. Unlocking their secrets might provide insights into the possibility of life on other planets or moons, water worlds that may play host to similar vent systems. Vents like these form as the rifting of tectonic plates allows hot magma from deep within the Earth to rise closer to the surface. The seabed, where seawater becomes superheated and takes up minerals from surrounding rocks, creates a mineral-rich fluid. This fluid jets back into the ocean at extremely high velocities and temperatures exceeding 400 degrees Celsius, mixing with cold seawater and precipitating dissolved minerals out in smoke-like billows. The chemicals here ignite a process that mirrors photosynthesis, where chemical energy, instead of energy from the sun, enables primary production via chemosynthesis. Because of this, life doesn't just survive here, it thrives in the depths. Vents stand as otherworldly oases, offering a glimpse of the resilience and adaptability of life on Earth to even the most extreme environments. In 2023, entirely new vent fields were discovered during Failure 2's inaugural expedition. These may not have been the type of vents they sought, but when it comes to exploring a place as mystifying as the deep ocean, you might not always find what you're looking for, but you're bound to discover something just as remarkable. Hydrothermal vents have been known to science since 1977, but a number of mysteries endure surrounding the origins of their communities. Over geological timescales, they are ephemeral, bound to the destructive influence of eruptions and earthquakes. So how can it be that no matter where they form, a diverse biological hotspot almost always follows? Dr. Monica Bright of the University of Vienna hypothesized that the answer lies beneath the seafloor, where the existence of a proposed subsurface ecosystem hidden from view might allow animals to pass between vent fields and colonize these puzzling worlds. We journey now from the mid-Atlantic ridge to the East Pacific Rise, where in August, Monica and her team set out on Failure 2 to test this hypothesis and seek out the proposed underworld of hydrothermal vents, should one exist at Music. All this is the Tikka vent site, one of the most studied in the world. In 2005, it was destroyed by a volcanic eruption, but in the years since, follow-up expeditions began to investigate the recovery and primary succession of animal communities at Tikka following such a large-scale ecosystem reset. Recovery had been quick. Tube worms, mussels, stalked barnacles and more had already recolonized and established themselves among the mineral spires. Music. Now, the team leading the 2023 mission with Schmid Ocean Institute hoped to find out how life had returned after the devastation. Vents at Tikka are home to a species that embodies all that is weird and wonderful about these alien habitats. Giant tube worms of the genus Riftia. They stand up to 3 meters tall, with a bright red branchial plume that channels chemicals from the vent fluid to colonies of bacteria that inhabit their tube or trophosome. The bacteria, in turn, convert these chemicals into food that sustains the worms, a perfect symbiotic partnership. While larvae of mussels and barnacles had been found in the seawater around the vents, the larvae of Riftia had never been sampled, pointing to a different method of dispersal so far undiscovered. Over the course of the expedition, Monica and her team dug deep to uncover the mystery of the subsea floor around Tikka, and what they found redefined our understanding of life and succession at deep-sea hotspots. We do not really fully understand how the animals that live there actually find this place and can come to this place. We looked for the first time into the subsurface life. Animals are able to live below the height of momentum, and this is, I think, mind-blowing. Now we know that, for example, tongas, they can colonize vents by traveling through the subsurface. This is the first finding. We know that these tube worms can live in this cave system. That's the second finding. And the third finding is that also the mobile vent founders can live in these subsurface areas. Such a method of dispersal is completely new to science, and it challenges the idea that most vent larvae rely on open ocean currents to disperse their young. But what the team discovered went above and beyond what had been hoped for. The beauty of all of this is also that the experiment itself was not even working so well. We kind of needed to be creative and, apply basically a new method. Flipping around the rocks opened our view into the underworld of hydrothermal vents. What we found was that we found even animals living below the surface. This expedition marked the discovery of a dynamic habitat, entirely new to science, existing in delicate unison with the vents above. If there's one thing the deep ocean has taught us in the relatively short time since the scientific community first plumbed its depths for life, it's that frontiers of biodiversity exist even in the places you'd least expect. Our oceans are home to countless species across divergent worlds, and yet much of their biodiversity is unknown. This knowledge gap stands in the way of fully comprehending the awesome power of life on Earth or the extent of human impact. In June, Failure 2 arrived in Costa Rica to investigate the biodiversity of an unprotected seamount where in 2013 an unusual discovery had been made. An estimated 100 female octopuses gathered at a small outcrop to brood their eggs. It became known as an octopus garden and hinted at the potentially rare and life-supporting role of seamounts such as this, where low-temperature venting might provide the perfect conditions for eggs to develop. But so far, no viable embryos had been found, leading scientists to wonder whether the site truly supported octopus development at all. If this phenomenon could be verified, it would make this nursery a feature worth protecting. Costa Rica is about 90% deep sea, and most of it has never been explored, so this expedition has been really critical on local levels, on regional levels, and on global levels. Costa Rica is actually going to be hosting in 2025 the United Nations Ocean Conference with Costa Rica in that leadership role. This cruise provides a brilliant opportunity to really allow us to take the science to decision makers at that forum and really put the deep sea center stage. For us, this cruise has been just an incredible success from day one. Verified a few of our hypotheses, and then a few more within days after that, which I can't say how rare that is in deep-sea exploration. The eggs were viable, which has just been mind-blowing. We found things we weren't expecting, like a skate nursery. We discovered a new low-temperature hydrothermal vent. It also has octopus brooding their eggs there. I was so excited, Beth was like, "Rachel, go outside and scream." I was bouncing off the walls. Brooding in this way is a labor of love for the females. It can take up to 5 years, and during this time they don't seem to feed much, if at all. It's thought to be their last mission, guarding their eggs to the very end of their life. But it's not in vain. Music. Witnessing babies hatching in real time confirmed to the science teams that the Dorado outcrop is indeed an active nursery. I'm just hatched and we're looking at a brand new baby octopus. Amazing! Happy birthday! Happy birthday! Oh look, we got an octopus shadow. This might be the only time in that octopus's life that it gets a shadow. Their findings at the site unveiled a deeper understanding of the life history of these octopuses and the ecological significance of seamounts. Technological innovation can unlock new ways of understanding the human effect. Since it was established, Schmid Ocean Institute has offered up its facilities and resources to the international scientific community at no cost to test new technologies and conduct groundbreaking research. In April, scientists aboard Fowler 2 set out to study the impact of climate change on deep-sea corals using a new technology called Solaris. These reefs are cities of life in the depths, hosting biodiversity akin to that which flourishes near the surface, though hidden away in the ocean's twilight zone. In these ethereal secret gardens, where sunlight dwindles to a mere glimmer, an array of corals and sponges build a complex home where other animals can shelter and find food. Squat lobsters cling to the coiling corals alongside brittle stars, making the most of these branching structures to reach into the flow of current, where faster-moving waters bring a feast of plankton and organic debris toward them. So we are off of the coast of Puerto Rico right now, and we're going to be exploring mesophotic and deep-sea corals along the west and southwest portion of Puerto Rico, and that's over off the deck. Are you fully submerged? My group studies a group of chemicals called the reactive oxygen species. We call them ROS, and ROS are oxygen intermediates. So you can think of them as a really reactive form of oxygen. What we have seen in shallow reef environments is that coral species that tend to be more resilient towards thermal stress, towards pathogen infection, have much higher concentrations of superoxide. So we believe that this is serving kind of like an armor. If these chemicals are in fact protecting corals, then we may be able to help corals armor themselves from stress by better understanding the controls that promote their formation. We have very few measurements of these chemicals within the ocean because they have a really short lifetime, so we don't really know why these corals are making them, which corals make these reactive oxygen species, at what concentrations. Is it toxic? At what concentrations? Is it beneficial? And we have this wonderful team of chemists, biologists and engineers all working together to try to understand this process that we know nothing about within the ocean. So, with the funding of Schmid Marine Technology Partners, Colleen Hansel's lab has been developing the first kind of series of in-situ reactive oxygen species sensors that can be used in aqueous environments. The way that we're monitoring the health of these corals is by using a sensor called DISCO. It measures these reactive compounds that these corals produce. In order to reach those deep-sea corals, we need to develop a whole different type of instrument. We couldn't take DISCO down to the bottom of the ocean. It doesn't have the right pressure tolerance, and it doesn't have the right kind of robust body to be strapped onto a submersible. As a result, Solaris was born. This has been a really great deployment of Solaris, highlighting its capabilities. Being able to span deep ocean research in deep ocean environments and ecosystems is exciting. What's really exciting is that this is going to springboard us into a whole new area of understanding the biogeochemistry of corals. It's been a really successful cruise. We collected around 300 specimens of corals and associated animals. We've actually collected 6 out of the 7 black coral families, probably somewhere in the realm of 15 to 20 species, some of which are absolutely going to be new to science. I think we haven't seen one like this yet. Some of the really interesting things that we found come to mind. A super high density of corals, a rich diversity, and we had this spectacular discovery of hydrocorals and stunning corals that was just super coral filled and totally unexpected. It's likely that we have multiple new species to be described, as well as information that could be very useful for proposing new marine protected areas. Vertical deep water coral reefs are areas where, essentially, corals live on the side of an underwater cliff. It's like walking in a forest and then suddenly the whole forest flips up on its side. Everything in that forest and everything that lives on those trees is still there, but completely turned around. That's pretty much how corals are organized along some of these underwater cliffs. If you can imagine that in a forest there was a wind always blowing, that's like the current we have underwater. And that current is what brings food and supports the animals and corals living across those vertical reefs. New advanced laser scanning technology allowed the team to produce highly detailed three-dimensional maps of the reef at a resolution of 2 millimeters, capable of identifying animals living in association with the coral. What we don't sometimes realize is that under the water we have this amazing topography. You have valleys, hills, mountains, ravines, crevasses and places where continental plates are rubbing against each other, creating entirely new spaces. It's a big three-dimensional connected area. I'm amazed that every time we put instruments in the water and have a chance to go deeper than we've been, we always find something new. From the cliffside reefs to deep-sea vents, creating high-resolution maps documents their current condition in a slice of time. In October, teams on Unveiled 2 tested a different approach to seafloor mapping, interferometric synthetic aperture sonar, or INAS for short, a technology that uses sound to create pictures of seafloor features at resolutions far more detailed than typical approaches to creating bathymetric maps. Normally, you're often just lost and blind at the bottom of the ocean. Because we had the maps and the synthetic aperture sonar, we were able to drive with pinpoint accuracy to all the various spots we wanted to go. When you drive up to a vent with the ROV, everything's dark. But as you get closer, things start to slowly illuminate. The first thing you always see when you approach a hydrothermal vent is the bacterial mats. And just like that, we found 7 or 8 actively venting complexes, towers 10, 12, 15 meters tall. The highest temperature was over 250 degrees Celsius, with tube worms and all the animals. That really validated our approach. We can now see if a vent is active or inactive simply from the SAS data. Knowing the texture of the seafloor will give you information on what types of animals can live there. This could really change our understanding of the distributions of different animals and how ecosystems function. I've been in the business for 30 years, exploring the ocean floor for precisely these sorts of environments. In the early days, we would spend weeks upon weeks hoping that we might encounter just one site. What INAS has done, and also the M3 multibeam mapping, is allowed us to identify the targets before we even go into the water. Now that we know we can do this, there's no going back. We've discovered the value of INAS and the M3 high-resolution mapping, whether there were hydrothermal vents or not. It's just that we got the double benefit of having this technology in the right place at the right time to discover the hydrothermal activity we did. Creating such detailed maps of regions like inactive vents allows us to better understand the biodiversity of sites targeted by the emerging deep-sea mining industry, which aims to extract valuable rare earth metals from these sites. Science and ecology have the opportunity to lead the way. Most of the ocean has been mapped with technologies like satellite systems using radar, but those give you very coarse resolution data. We can then improve on that by using vessel-mounted multibeam, which gives us better data, but it's still relatively coarse. We've been improving that by putting systems on board the ROV, allowing us to understand the morphology of the seafloor. With SAS, we can get one order of magnitude more detail. This is really high resolution. It's getting to the point where we can see some of the geological features directly in the imagery. We can then overlay photomosaics on that, which will give us millimeter resolution. We can start to build up a nested approach from satellite bathymetry right down to very detailed information about specific ecosystems. The applications of INAS, from understanding deep biodiversity to tracking fine-scale human impacts, make this a revolutionary tool in understanding the deep-sea floor, but there's still a long way to go. It's a common misconception that exploring the ocean is a far simpler endeavor than space exploration. But this couldn't be further from the truth. We can't point a telescope at the waves and see what lies below, for the water conceals from view canyons and ranges that rival anything seen on land. We have to enter the depths to unlock its mysteries. The ocean does not give up its secrets easily. When you're exploring the deep, where the lights of an underwater robot may light up a stretch of seafloor just tens of meters ahead, you can never be certain what new discoveries lurk beyond the wall of darkness. Sometimes there are clues, though. It takes a keen eye and an intimate knowledge of the depths to spot them. In August, Chief Scientist Dr. Roxanne Binart and her team were on a mission to uncover the mysteries of unexplored vents at the Western Galapagos Spreading Center, a site just a few hundred kilometers from the eastern side. This is the very region where scientists first discovered hydrothermal vents. In 1977, the scientists hoped to characterize the unique communities on the western side and search for more undetected vents. After hours of searching a seemingly barren seafloor, it was the appearance of a trail of squat lobsters that hinted at the presence of a new vent. Finally, right as I was about to go to bed, we started seeing a lot of squat lobsters, and we started noticing a lot of fissures and faulting. It did feel like the squat lobsters were leading us like breadcrumbs, as if we were Hansel and Gretel, to the actual vent site. Looking good now, you platform out. When we were looking for vents from the surface, it's the equivalent of being on Mount Olympus and looking for a football post. The first thing we saw was a big group of riftia that popped up on the screen, which is unmistakably a hydrothermal field. I was standing right next to Roxanne, so we both smiled and looked at each other and said, "We found it, it's right there." These are unique ecosystems that are unlike anything else on Earth, and we're still only now trying to understand what shapes them. The trail led them to a vent field that was new to science at around 2,800 meters down, one of many discovered on Unveil 2 since March. We've successfully sampled across multiple disciplines at the sites, ranging from chemistry to geology to biology. We've collected the first ever high-temperature water samples, and we've been able to build the most comprehensive dataset ever for this location. 80% of our planet's living space is the deep sea. And that means 80% of our planet's living space never experiences sunlight. It's astonishing to think that the other 20% contains everything else. Every rainforest, every desert, Paris, Los Angeles, you name it. All of it is in that other 20%. It gives you a sense of just how much of our planet is deep sea. The deep ocean may be far away and out of sight, but it is not separate from our world. In fact, it is, in many ways, the single most important component of our planet's biosphere. Its processes shape the conditions of our climate, and ecosystems concealed away in a world of darkness and mystery play their part in defining the ecology of entire oceans. We know more about most of the planets in our solar system than we do about the deep ocean. But the reason isn't because we haven't been curious. The reason is because we haven't had the tools to go down and look. We have them now. The truth is, every incremental step that we take to learn more about the deep ocean helps us understand more about the entire planet. What is the driver to get us to see? Somehow there's something about going into another world that is truly exhilarating. It's a world we don't belong in, and yet you realize how connected you are to it. We need to care about every part from top to bottom, from what's happening in the atmosphere to what we're doing on land, how we affect the deep ocean, and how the deep ocean affects us, which it does. Keeping those connections safe is what will keep us alive on this planet. In just 10 months, Unveil 2 traveled more than 39,000 kilometers, allowing scientists to uncover new species, ecosystems and discoveries in locations spanning both the Pacific and Atlantic Oceans. Science teams mapped 190,000 square kilometers of seafloor, including cold water reefs, seamounts and 5 new hydrothermal vent fields. In this world of wonder, once thought barren and devoid of life, Schmidt Ocean Institute and Unveil 2 have, in 2023, forged ahead to unlock its mysteries and bring the deep's marvelous complexity to light. But they aren't stopping there. For years to come, this beacon of discovery will continue to lead a new chapter in the story of deep-sea exploration.